Okay, so from the last video, if you recall, we had set up our odds ratio to work on individual elements. But now, using these vector type arguments, we can vectorize essentially that function and operate on a vector rather than an element. So here, let's say we want to apply this odds ratio, and it's created to just operate on one 2x2 table. That's the assumed design of the function. So what if we had 5 2x2 tables and we want the same output for each of the separate 2x2 tables individually? So first we're going to just create, notice this is just using the rep function, and we're going to create some tables with data that's just randomly generated. Go through and make sure you understand this. This is creating for randomly generated Poisson random variates with lambda rate parameter lambda equal to 10, and it's going to put it in a 2x2 table. It's going to do that 5 times. Okay, so simple enough to code. Now let's lapply. So remember, list apply will apply that across elements of a list. For the, here's our object that we're going to apply the function odds ratio to. So this is going to do it separately for each of those 5 2x2 tables. The result will be in result. Okay, so then we can take result and pull out just the odds ratio if we want to see that. All that this function does, notice FUN is the argument for lapply, and that just specifies the function. We can use a user-defined function right here. I do this a lot if it's a kind of a dumb function like this, where it's just a really quick and easy way to do something. Here I want to take whatever my result is and pull off the estimated odds ratio. So it's not like I'm going to use this in any other context, so why not just apply it here within the lapply function call? So we're going to unlist those results, and that just puts it into a vector format object within R. Make sure you can understand that. Go step by step through this. Make sure you understand why it looks like what it does, and at the end you should just see a vector of these estimated odds ratios. Okay, so again, from the second set of notes, we talked a lot about the apply function and how important it is. Remember, the specifications of that apply function are the object that we're going to operate on, the margin for which we're going to operate for that object, and finally the function. The function argument, like we saw in the past slide, can be anything. It can be a user-defined function, or it can be a default R function. It's up to us. Generally, apply only passes the function one argument and the vectors by the vectors supplied by margin. We can, though, use the apply function to pass other additional arguments. So for example, here I have a matrix defined. Notice it's just a 3x4 matrix of some 12 sample values from the vector 1 to 100. Then we're going to use the apply function to just calculate the mean of each column. Then we're going to do the same thing, but now we're going to use a user-defined function. So this is doing a sample variance calculation here across each column again. Finally, we could use, recall that central function we'd used before. Well, remember, to use the central function, it can operate upon the margins, those column margins of our vector A, but we have to specify what measure we want reported. So it could have been geometric or median. Well, we're going to do mean here, so we could apply it that way. Notice that this is an argument of our function central, so it belongs in the ... following the function call. If you try to put measure ahead of time, it will work if you name it. If you do not label it with measure, I doubt it would work. I just always leave them for the end. Keep it simple, and you know it'll always work. All right, so we can also declare our own binary operators, which I think is pretty cool. I mean, but why not? We can define our own functions, so why not our own binary operators? So recall a binary operator such as this, which does true matrix multiplication. This is actually just a function which has this call. That's a weird looking function call, isn't it? But that is a function call. And you have arguments x and y, which are both matrix arguments. So notice, if we have a and b, which are both the same 1 to 4 values, 2 by 2 matrices, we can multiply them. And this is how we've always used it in the past. Or we can run a and b through a function call using that function name. We get the same thing because this is a binary operator that's actually derived from the function call. But what's great is we can define our own binary operators. So any function object with a name having a pattern like this, %text %, can be evaluated this way as a function call. So notice if I create a new function, so notice I'm using that function syntax right there for the binary operator call, and I'm going to call it within the little single quotation marks %nic %, and we're going to make it the function just simple, x caret top y. Okay, so we're exponentiating with to a power of y. Then what's really great is then we can call 3 %nic %2, and what do we get? 3 squared. So 3 is the x, the first value that we operate on, and 2 is the y. So just like we could do that here, a, b, well, those are just the 2 arguments in order of our function version of that call. So that's nice. And if you're going to do a certain calculation over and over, I would create it this way as a binary call so you can just operate on your objects directly and you don't have to call it as a function type call. But there are advantages to functions. They're really useful. I use them almost every time I program in R. Or create my own function, I should say, almost every time I program in R. You can get more compact code. So if you have a long piece of code that does multiple calculations, chunk it up into functions. Just write functions to perform each task, even the smallest of tasks, then it's more transparent. And you can also identify errors more easily. If you have 1,000 lines of code to run a very complicated process and you haven't chunked it up by functions, it's going to be very hard to go through and debug your code, and you will need to debug your code. So why not be able to debug each function separately and kind of break it up into smaller tasks that way? It's just very reasonable to take that approach. A well-written function is more trustworthy and more transparent than having a long list of expressions in general. I do not like going through code where there's 100 lines of code. I'd much rather see functions called where I can go look at the function and think, okay, well, what's that function doing and how is it being operated upon and how is it using the results? That to me is a lot more interpretable in the end. It's easier to interact through a function than to type lots of code. Again, it's about transparency there, I think. Function computations are performed locally. So remember, when you're in a function call, the objects that you operate on within the function are locally defined. If they're not defined locally, then it defaults to the global. But that's better actually for doing really long, complicated processes, because if you have 1,000 lines of code, it might happen that you name 2 things X and you forget about that you had something previously defined X. Well, globally, X has changed, but if you have it operating on within a function, then locally it hasn't, and you'll still get the correct result within your function. So another reason to make sure you use functions. It is the most convenient way to share programs. So I have given functions out to people, and for some research papers, I've written functions and people have emailed me and I share my functions with them. That's one of the beauties of R, I think. A well-written function can be adapted to multiple situations. So I actually do this. There are some R-defined functions that I've written my own version of to kind of tweak a certain methodology. I want to do something a little bit different than what the author of the function did, so I create my own version of that function, save it, source it when I need it, and then I've got my own tweaked version of whatever that process is. Okay, so if we're going to write functions, we need to do so in a way that makes sense. A function is going to be well-defined when the value returned by your function is completely determined by the function's arguments. You don't want to rely upon global variables. So remember that function before where I defined an x and a y locally, but it used a global value for z? That was poorly written. That was not well-defined. Don't do that. Make sure if you're going to use values x, y, and z, make sure that those are arguments in your function. A function should not affect later computations or other function calls. So if you, for example, options, open close parentheses will set your global parameters, but options can be set also within the local environment in a function. So your computations within one function could also make an effect on other functions, and you don't want that to be the case. So don't change global settings within a function as a rule of thumb. Functions should be transparent and have well-documented code. When you turn in functions to me, I want you to be transparent in what you did and use comments to do that. And there's nothing wrong with writing trivial functions that are not well designed. Sometimes I do that all the time, to tell you the truth. If I'm just going to use a function a couple of times, I don't go to the trouble to do everything that I'm telling you here. It's just when you're going to share a function that you need to make sure it's well defined. Okay, so below are two functions for calculating the log likelihood of an exponential random sample. The log likelihood is a function of the parameters, so you can define, if you're in mathematical statistics, you understand how to derive a log likelihood function for a particular probability density function. And this is how you could implement it computationally within R. So notice here that the first function is going to be a function of theta, your parameter vector. However, this function is not going to be well defined because it's going to cause some changes in future computations. And also, there's no comments here to describe what's going on. So let's take a real quick look at it. Notice theta is your argument that you pass in. So if we look at arguments theta, the calculation only needs to include 3 significant places past the decimal, but you don't want to change your global option within a function because remember that will change your global settings, and that's not good, a well-defined function. Then it reports back LL, your log likelihood function, but it's using X. And what is X? Well, it depends on what globally X is. So again, not well defined. So here we defined X globally. We call this version of the log likelihood function for the exponential probability distribution, and we put in a rate of 3. All right, so what is X? Is it clear to you? You could go in and debug the function, but you'd have to go in and step through that function to make sure it's operating on the right X. If you call X directly before that, that's fine. But if you're calling this out of context of how you've defined X, it's not clear that X is going to be what we think it is. Then we could compute the variance of X, but using 7 significant digits, is that going to take effect given that we changed the global options for digits? So it's not clear. So let's reset everything. So this call options defaults just restores all the default options within R, which is a good thing to do if you've run something like that. And here's a good version of the function, a well-defined version of this. Notice we pass in X and theta, important. We compute the log likelihood, and then we just print it. So this is not changing any global options, it's just printing it out with 3 digits rather than changing the global options. This is much better.